Hello, my name is Mike Buller, and this video explores some of the fundamental principles relating to structural analysis and design. Consider a continuous beam supported at one end by a pin and continuous over two roller supports. Additionally, the beam has an internal pin. The beam is subjected to two partially distributed loads, two vertical point loads, and one inclined point load to the end of a 3.75 metre cantilever. The first thing to do in any problem such as this is to determine the number of unknowns. So if we consider in turn each of the supports, the pin support to the left hand end has two unknowns associated with it. That is the vertical reaction and the horizontal reaction. Each of the two rollers has just a vertical unknown associated with them. So in all, this particular beam has a total of 4 unknowns. For a simply supported beam, we would normally consider the 3 equations of equilibrium. These are the sum of the moment equals 0, the sum of the vertical actions equals 0, and the sum of the horizontal actions equals 0. In this instance, we have an internal pin. So we have a pin partway down the length of the beam. We know that for a pin, we can say the sum of the moments equals 0. So it is true to say that the sum of the moments at the pin equal 0. Given this, we now have effectively 4 equations of equilibrium and we have 4 unknowns. So we can say that in this instance the beam is statically determinate. Once we have determined that the beam is statically determinate, we can go on and construct the free body diagram. Because we have a pin, an internal pin in the beam, we can effectively split the beam into 2 halves. If we take the first part of the beam to be from the pin support to the left hand side to the internal pin, and the second part to be from the internal pin to the end of the cantilever. We can first add our vertical and horizontal actions associated with the supports to these 2 partial beam diagrams. So to the pin support we have a vertical action and a horizontal action. And to the first roller we have just a vertical reaction. To the second part of the beam we have a roller at the end of the cantilever. So we have a roller supporting the beam at 3.75 meters from the end of the second part of the beam. Now thinking about just the second part of the beam, that is statically indeterminate because we have one reaction or one action and we have 3 equations of equilibrium. So that structure in its own right would be unstable. In order to make it stable, in order to make it act in equilibrium, we add another vertical support and a horizontal action. This vertical support we will call VP. So we've got VP. And the horizontal action at this point we will call HP. And if we give the rest of the supports their names, we have the vertical action at A and the horizontal action at A, the vertical reaction at B, and the vertical reaction at C. In order to maintain static equilibrium at the pin, we apply a point load to the end of the cantilever beam. This is of equal magnitude to VP, but acts in the opposite direction. This vertical action acts as a point load to the end of the cantilever, so we can call this PL, and it's due to the pin. Additionally, in order to maintain horizontal equilibrium, there has to be a horizontal action on the end of part A of the beam of equal magnitude to HP, but acting in the opposite direction. So we can say that this action here is also HP. That is the first part of your free body diagram. To this we then add the loads. So firstly, on part A of the beam we have a UD load. We also have a UD load to part B of the beam. In addition to the two UD loads, we have a point load, again acting at the pin, so we have a point load acting at the pin. Note, we will only apply that once. Now you can apply that to either part of the beam, it doesn't make any difference, but you only apply it once. So I'm going to apply it to the end of the cantilever. Additionally, we have a point load part way down the length of part B, and we have the inclined point load to the end of the cantilever. The last part of the free body diagrams is to indicate the dimensions and the magnitude of the loads. We now have our free body diagrams, one for part A and one for part B of the beam. Before we go any further, there are three assumptions that we are going to make. Firstly, any vertical load that is acting upwards we are going to assume is positive. Any horizontal load acting from left to right, again, we are going to assume that is positive. And any moment acting about a point that is clockwise, we are again going to assume the moment is positive. So those three assumptions you need to bear in mind as we go through and calculate the vertical and horizontal reactions associated with this beam. So taking part B to start off with, and the reason we consider part B is that part A has a point load to the end of it. The reason we consider part B is that we have to calculate the vertical reaction of the pin first, because that is applied to part A of the beam. So taking part B, firstly we need to resolve the inclined point load to the end of the cantilever. So we need to resolve it into its vertical and horizontal components. So for the horizontal component of the point load, PH, and that equals the cosine, so it's the cos of the angle, 60 degrees, times the magnitude of the load, and the load is minus 20 kilonewtons, and that equals minus 10 kilonewtons. And for the vertical component, so PV, it's going to be the sine of 60, and that's times 20. I'm ignoring the sine in this instance, and I will explain why in a minute. So it's the sine of the angle times the magnitude of the load, and that equals 17.32 kilonewtons. The reason I'm ignoring the sine of the load is because when I take moments, I will assume that everything acting clockwise is going to be positive. So that's why I've taken it as being a positive load. We can now go on and calculate the vertical reactions at VC and VP. So firstly, we are going to consider taking moments about the pin. That will effectively give us the vertical reaction at C. If we consider our equations of equilibrium, we can say that the sum of the moment at the pin equals 0. And we are going to assume, as I said earlier on, that everything acting clockwise about the pin is going to be positive. So let's consider the loads one at a time. Firstly, we'll take the vertical component of the point load to the end of the cantilever. So we have our pin, we have our beam, and we have the vertical component of that point load, 17.32. And that is acting clockwise about the pin. It is positive. That's why I ignored the sign earlier on. So we can write positive 17.32 times its lever arm, and its lever arm is the perpendicular distance from the pin to the point load. So that's the perpendicular distance, and that is 8.25 meters. So we have 17.32 times its distance, 8.25, and that takes care of the point load. We also have the second point load, the 15 kilonewtons. So again, that's your pin. So this is the pin in each case. This is VP. We have a point load, again, acting on the beam, 15 kilonewtons. And again, it is going to try and rotate the beam in a clockwise direction about the pin. So again, we can say that's positive. So we have plus 15 times its distance, 3.5. And again, that takes care of that particular point load. The other load we have is the UD load. So again, we'll have a pin, there's VP. There's a section of the beam, and we have a UD load acting along part of that beam, and that is 10 kilonewtons per meter. And as with the others, that is trying to rotate the beam in a clockwise direction, so it is positive. So we can say plus the UD load, and that is 10. That's the magnitude of the load times the distance over which it acts, which is a total of 4.5 meters, times its lever arm, 4.5 over 2. And you should know by now that the resultant force associated with a UD load acts at the centroid of the UD load. Hence the lever arm is the length of the UD load over 2. So in this case that's going to be 2.25 meters, given an overall load that's 4.5 meters long. The last load acting is the vertical support associated with the roller at C. So we have our beam, we have the vertical reaction, that's VC, and we have a distance, and the distance of VC is 4.5 meters. In this case, this is acting anti-clockwise, so it is trying to turn the beam in an anti-clockwise direction. It is therefore negative. So we can say minus 4.5, that's the lever arm, VC. So minus 4.5 VC. And going back to our equations of equilibrium, the sum of the moments equals 0, so we can state that that lot all equates to 0. And if we simplify that, we will end up with 296.64 minus 4.5 VC equals 0, and that gives a vertical reaction at C that equals 65.9 kilonewtons. So that's the vertical reaction at C. Now we have to consider the sum of the vertical loads. So we want the vertical reaction at P at the pin. So to get that, we consider the sum of the vertical loads equals 0. And we can say that VP plus VC minus the sum of the point loads minus the sum of the UD loads equals 0. And if we go on and put some numbers into that, VP is what we're trying to calculate, so that is still an unknown, plus VC, 65.9, minus the sum of all the point loads coming down. So we have 17.32, that is the point load at the end of the cantilever, and we have the 15 kilonewton point load part way down the beam. Those are the two vertical point loads. They are negative because they are acting down. We also have the UD load, that is negative as well, so that's minus 10 times 4.5, and all of that again equals 0. And if we go on and simplify that, you should find that VP, the vertical reaction at the pin, equals 11.4 kilonewtons. We can now go on and consider part A of the beam. And we can say that PL at the pin, so the point load at the pin, that, if you recall, is equal to a VP, and that equals 11.4 kilonewtons. As I say, that is to maintain static equilibrium of the pin, and as Mr. Newton said, every action has an equal and opposite reaction. So the vertical action at the pin, the support of the pin, has to be opposed by an equal and opposite point load at the pin to effectively cancel each other out, so you maintain static equilibrium of the pin. As with part B, we can now go on and take moments about A to give the reaction at B, and we can say that the sum of the moments at A equal 0, and as per before, we are going to assume that clockwise is positive. So we can consider the loads in turn. So for the point load and the point load at the pin, we have A here, so that's the support at A. We have your beam, we have the point load, and we also have the load from the pin. So the point load from the pin is 11.4 kilonewtons, and the original point load to the beam was 12 kilonewtons. These are both acting the same way. They are acting clockwise about the pin, so they are both taken as being positive. And their lever arm, again, is the perpendicular distance from the point of interest to the 2 point loads, and that is 7.1 meters. So for the first part of this, we have positive, because they're going clockwise, 23.4 times 7.1. That's for the point loads. Now we can go on and consider the UD loads. So again, we have our beam, and on this we have a UD load to the full length. So this is A, and your UD load is 6 kilonewtons per meter. And again, it is acting in a clockwise direction. It is trying to rotate the beam in a clockwise direction about A, so we can say it's positive. So it's plus the magnitude of the UD load, 6, times the distance over which it acts, 7.1 meters, times its lever arm, 7.1 over 2. And again, just so you're sure, the lever arm, the distance from the centroid to the point about which we're taking moments, that is 7.1 over 2. So that is your two primary loads. We also, as previously, we have to consider the reaction at B. So again, we have point A, we have our beam, we have the vertical support at B acting up. That is trying to go anti-clockwise this time. So it's trying to rotate the beam about A in an anti-clockwise direction. So that is now negative. So we can say it's minus 5.75 VB. And as before, that all equals 0. And we can simplify that to give VB equals 55.2 kilonewtons. And the next part, again, considering one of our equations of equilibrium, we can say the sum of the vertical forces equals 0. Therefore, VA plus VB minus the sum of the point loads minus the sum of the UD loads, that equals 0. So again, if we give this some numbers, VA is the unknown, plus 55.2 minus the sum of the point loads, so we've got minus 23.4, minus the sum of the UD loads. So we have the magnitude of the UD load times the distance over which it acts, and that equals 0. And then if we simplify that, VA equals 10.8 kilonewtons. And the last bit, if we just scroll back up to the top, we have to resolve the horizontal actions. So one of our equations of equilibrium was that the sum of the horizontal forces equals 0. So we have a horizontal action acting on the end of the beam, that is the horizontal component of the 20 kilonewtons. It acts in a negative direction, so it's acting from right to left, that's 10 kilonewtons. To maintain static equilibrium of part B, HP to the left-hand end of part B, that has to equal positive 10 kilonewtons. That is then applied to the end of part A as minus 10 kilonewtons. And again, for static equilibrium, HA must equal 10 kilonewtons. I hope you have found this video useful. If you have any comments or suggestions, please do send me an email at the address shown on screen. Thank you for watching.